Hello and welcome everybody, my name is Selma Yasser and I'm going to talk about data compression. This video is just an introductory video to data compression. It doesn't cover everything, so let's get started. What we're going to talk about in this video is what is data compression. What is the difference between lossy and lossless compression? And a few types of compressions such as the run length encoding system, the negative compression, and the dictionary encoding. One of the types of the dictionary encoding is called the LZW encoding, and we are going to talk a little bit about that. So let's get started. Firstly, what is data compression? Well, data compression, it is the process of encoding a data to reduce the size of that data. So, for example, if you have a file, it can be either a picture or a text or anything, and that file is way too big and you want to save it somehow on your desktop. You will basically need to compress the file in order to save it. You want to reduce that file size. That will be done by data compression. For example, if that one word requires 3 bytes, if you compress that data, then it might require only 1 byte. We have the original file. It will go through some encoding process and it will come out as a compressed file. The input is the original file and the output is the compressed file. We have two different types of compressions, the lossy and the lossless. Now, what exactly is the difference between them? Well, when the data is decompressed, the opposite of compression is decompression. Basically, when you have the file, when you have the compressed file, and it goes through decompressing process, and then you'll get the original file back. That is the meaning of decompression. So basically, what you're saying here is that when you have a file and you decompress that file, if the information is still the same as it is and there is no loss in any information or in any data in that file, that is a lossless compression. But if you do find a loss in the information, then we call that a lossy compression. Now you might ask, how can a piece of information or a piece of data lose its information? Is that even possible? Well, yes, that is required for the compression. If you have a lossless compression, such as a text, well, you can't really lose any information in that. You can't just write an entire paragraph and find that you have a word missing or something. That is not possible, so a text file is a type of lossless compression. If you write the number 5 or number 1,000, for example, 10,000, and you open in a file and you reopen that file again, then you don't want to see that number decreasing to 3. It's simply not possible as well. So this is a type of lossless compression as well. But if you're going to talk about lossy compressions, well, lossy compressions occurs when you have, for example, a picture or a drawing or something. Then what will happen is that if you have two colors that are similar, then the compressor might just take those two colors and get their average, or the average color between them. If I have, for example, this shade of red and a really darker shade of red, even though they both kind of look the same right now, but yeah, then it might just turn them both into red to save more memory or to save more space. To sum up exactly, the difference between lossless compression and lossy compression is that in the lossless compression, if you decompress a file, then you will get the same file as it is, and there will be no change in information. But in the lossy compression, if you decompress the file, then you will find that some information are missing. Now it will not be, of course, it will not be visible for you, and you might not even notice that the information is missing. But for the computer, it will know that you have compressed that file and you have reduced the size by removing some information from it. Now we will get into the types of encoding. And our first type is the run length encoding. Well, run length encoding is a lossless compression, where data is compressed in a way such that it represents the data and how many times it is repeated. Well, let me explain what that means. Over here, we have a piece of data, just random text files or random alphabets next to each other. If I want to compress that using the run length encoding system, I would look at the first type of data, which is an A. And then I will count how many A's are there. There is 1, 2, 3, and 4. So instead of writing the 4 A's, I can just say it is 4 A. So we have 4 A's. Looking at the next one, we have a B. So 1, 2, 3, 4, 5, 6. We have 6 B's. If we were to look at the C's, this is a C. Then we have 1, 2, 3, 4, 5. So 5C. And so on. So basically, this run length encoding represents a type of data. What is that type of data? We will say it's an A. It can be an integer. It can be a string. As we see here, A is a type of a string. It can also be an integer. And then we will see how many times that data is being repeated. Here it is repeated 4 times. The A is repeated 4. The B is repeated 6 times. The C is repeated 5 times, and so on. This is the type of encoding called the run length encoding. For example, if we're going to talk about a picture, and we have this picture drawn here, and we'll just imagine, okay, that for example this is black and black, then we have 3 blacks, we have 1, and we have 2. If I were to say that, for example, if I were to represent this in data compression, then I would say we have 1 white, and then we have 2 blacks. Then here we have 3 blacks. Here we have 2 white and 1 black. And here we have 2 black squares and 1 white square. This is one way of representing an image in the run length encoding. Now, of course, it's not really written as W and B in the encoding system, but I'm just doing that for simplification. So run length encoding. Run length encoding is very useful, but we don't use it all the time. There are times where run length encoding is insufficient. We call these insufficient run encoding times negative compressions. It is basically when the run length encoding occurs, when you do a run length encoding system, and that bit pattern is more than the original pattern. When you compress a file and you find that the compressed file has a bigger size than the original file, and that is what we call a negative compression. This can occur in run length encoding. Here we have an uncompressed text, which has A, B, B, C, C, D, E, and so on. If we compress it, we take the first one, which is an A. So we see 1A, because there's only 1 A. Then we look at the second one. This is a B. There is 1, 2. 2 B's. Then look at the second one. The third one now. This is a C. So how many C's? 1, 2. So 2 C's. Then we look at this one, which is a D. And how many is that? We have 1 D. And so on. If we do this, if we do the compression for this, then we will find that this is the compressed file. And you will notice here that the compressed file looks bigger than the uncompressed file. This is what you call a negative compression. So basically, when is it good to use the run length encoding? Well, to answer that question, we can say that run length encoding is best to use when you have repeated patterns next to each other. So if you look back at this one, we see that we have a couple of A's repeated and then B's and C's and D's and E's. It's a lot. There are a lot repeated. But if we look here, we will notice that we have only one pattern, one item, and then next to it there is another one. And that keeps on changing. So here it is not useful at all to use the run length encoding. And now we will look at another type of compression, which is called the dictionary encoding compression. Well, to start off, the dictionary encoding compression is a lossless data compression, which means that once it takes the data and decompresses it, once it takes the compressed file and decompresses it, you'll get the original file back with no loss of information. And how does that work? Well, the dictionary stores an entry, such as a word, for example. It can store a word and refer to it with an integer. For example, if you have a dictionary, let's call it dict, and it includes the value high, we will refer to it as 1. So now we have high as an entry. It's referred to as 1 inside the dictionary. Every time I write high in a text file, once the text file is compressed, it will give the value 1. And that will save a lot of space since high consists of H and I. H in the ASCII table takes 7 bits, and I in the ASCII table takes 7 bits as well. So if both of them are referred to, so if HI, which is high, is referred to 1, that will take a lower number of bits. Instead of it taking 14 bits, now it only takes 1 bit. And this is just an example that I'm giving, not the actual value. So that's how it kind of works. If I put another value, for example, such as by, and I let that value refer to 3, for example, every time I write the word by, it will change to 3 in the compressed file. So the compressed file will not save the entire value of by, but it will save the value 3. This will get us to a type of dictionary encoding, which is called the LZW encoding. The LZW is a type of dictionary encoding which uses adaptive dictionary during the encoding process, which means during the encoding process, the dictionary will keep on changing and updating. Let's look at an example here. We have our own dictionary, which is called, which has the value of space, which is 0. So every time I see a space, it will be replaced with a 0. And then we have the value A, which is stored as 1. And we have the value B, which is stored as 2. So if we look at the dictionary over here, if you look at the word text over here, we have A. So instead of it taking 7 bits, as in the ASCII, here it's referred to as 1. So it will be 1. Then we have B. Is it in the dictionary? Yes, it is. It's in the dictionary and referred to as 2. So we will put it here, 2. Now we have AAB. This is one entire string. Is that entire string inside the dictionary? No, it's not. We only have space A and B. So it will add it as the numbers that each letter refers to it. A refers to 1, so 1, 1, and B refers to 2, so 2. Then it will go to the next one. By the way, I forgot to add the space here. There's supposed to be a 0 and a 0. And then after the AAB, there is a space, so I should add a 0 here as well. And then we have BBA. Is BBA inside the dictionary? Well, it's not. But what do we have? We have each letter individually. So it will add each letter, it will add each number corresponding to the letter. Then we'll have 2, 2, since B corresponds to 2, and A is 1. Then we have 1. Then we have a space here, so it will be a 0. But look at that. Since we already have AAB and BBA, we don't know their value, their values don't exist in the dictionary, then the LZW is an adaptive dictionary, which will cause these values to be added inside the dictionary. As you see here, the last letter we have is B, which is 2. After 2 comes 3. This is the next number. So it will add AAB to the number after the last number. The last number we have here is 2. So AAB will be referred to as 3. Then we have BBA. BBA will be referred to as 4. The dictionary during the encoding process, during the reading of each and every element and string, it is changing the dictionary and updating it. Here it added AAB and then it added BBE, two numbers after the last number, which was 2. Now it became 3 and then 4. So now every time it sees a BBA, it will add 4. And every time it sees a AAB, it will add 3. Let's try. After the space here, we have B, B, A. So B, B, A, which is 4, since it is written in the dictionary. And then we have space, which is 0. And we have AAB. Do we need to add each and every entry again, such as 112? We don't, because this is considered as one entire word inside the dictionary, and it is saved here too, as the number 3. This is the LZW encoding system. It keeps on changing during the process. If the value is not already inside the dictionary, then once you leave a space, it will put it or add it inside the dictionary. Here it considered BBA as one word because you left a space after it, and AAB as another word because you left a space after it, and there is a space before it. So these two are considered two different words. And that's it for the LZW encoding, and that's all for this video.
In the next video, we will implement some of these compressions in Python. And we'll also look at image, video, and audio compressions.
So thank you for watching, and I hope I see you again next time.